Welcome back, Physics 1. We are continuing in our discussion of collisions, moving on to an example. We had been talking about particle collisions, so now we're going to look at the elastic collision between two identical billiard balls. So if you recall back, I talked about how billiard balls, not truly inelastic, but pretty darn close. And normally here's where I would say your homework is to go play pool, but that would involve not socially distancing, so don't play pool unless you've got a pool table and you can play with members of your immediate family, in which case do that, because we all need some stress relief in life. So we've got two identical billiard balls. One is initially at rest. So we've got our mass, P1 coming in to strike the other one. Okay, so they hit, pow, and then we have P4, P3, that is a P, not a B, and you've got some angle A between them. So this is the story we're telling. Okay, so I stated this, I will write this. We will assume elastic enough, and we can show angle A is 90 degrees. Okay, so let's start with the conservation of momentum. To get to kinetic energy, we will need P squared. So the reason why we need both is because momentum can get us kinetic energy and vice versa. Okay, so we can get P squared with a dot product, which you guys are all experts in right now. So P1 squared is equal to P1 dotted with P1 is equal to P3 plus P4 dotted with P3 plus P4 from this. And all of this is equal to P3 squared plus P4 squared plus 2 P3 P4 cosine of A. Prove to yourself. Okay. So to finish the kinetic energy calculation, we can divide by 2m. So as long as you do it to everything, you're fine. So then we would have P1 squared over 2m is equal to P3 squared over 2m plus P4 squared over 2m plus 2P3, P3, P for cosine of A over 2m. This is K1, this is K3, this is K4. This, of course, is assuming low speeds, which if any of you are playing relativistic billiard balls, I want you to invite me because that would be really cool to see. Actually, the human eye couldn't perceive that. Still, I want to see it. Okay, so recall conservation of energy, which we're going to bring to play now, dictates K1 is equal to K3 plus K4. Remember, we stated it was elastic, so all we have is kinetic. Thus, cosine of A is either equal to 0 or A is equal to 90 degrees. So this works in low speed situations where neither P3 nor P4 is 0. Otherwise, so in the case 0 cosine A is equal to 0, cosine A is indeterminate. And there you have it. We have shown that the angle between them is 90 using the conservation of momentum and conservation of energy. All right, which leads me to a nice little discussion on impact parameter. Pow, pow, pow. So, the distance between centers perpendicular to velocity. So it's different to hit something straight on than to hit it like kind of off to the side. So it's not really at a different angle, it's just more off to the side. All right, so I draw pictures for this. So in pictures. And this is, of course, with billiard balls, essentially. So they weigh about the same. Okay, so we've got M coming in to strike M. And we've got this distance B. And so what's going to happen is this M is going to stay there, and this one's going to just roll right on by like nothing ever happened because the impact parameter is too large for them to actually strike each other. All right, so large B. We could also have M and so in this case, you've just basically, this ball is going to graze this ball. And you'll get small angle, very small momentum. And you could have M coming in not quite dead on, but really tiny b, hitting M, and you'll get much larger angle. Symmetric scattering. And then you can have a head-on. True head-on. B is 0. And what you can get there is that this one ends up being at rest, and all of the momentum has gone into this one. There you go. And so impact parameter is related to the size of the B, and these are the different implications for different impact parameters. So just to recap everything that we've talked about in terms of scattering, you need to look at both your momentum principle and the conservation of energy in order to go after it. And you need to ask questions about how can I go after kinetic energy and momentum. All right, so I think that wraps up part 2 of Monday's lecture. I will see you next time for Tuesday's lecture.